So it says the oxalic acid has the IUPAC name ethane dioic acid and a molar mass of 90 grams per mole. Okay, they have the molar mass and everything given. The name oxalic acid originated from the fact that it was first isolated from the plant of the genus Oxalis. The formation of oxalic acid in plants involve the hydrolysis of oxobutane dioic acid. They form oxalic acid by hydrolysis. Hydrolysis means though we are breaking a bond using water molecule. Plant can also form oxalic acid from glycolic acid. Plant can also form oxalic acid from glycolic acid. Okay. Oxalic acid can be manufactured by oxidizing sucrose using nitric acid in the presence of vanadium 5 oxide catalyst. 100,000 tons of oxalic acid are produced each year. Much of the oxalic acid produced is used for cleaning or bleaching because it converts insoluble iron compounds into soluble iron salt. Okay, we got that's the theory part. They are saying calculate the atomic economy by the mass of formation of oxalic acid from the hydrolysis of 2-oxobutane dioic acid. They are asking to find the atomic economy. That means they are talking about this equation. Right. So we know how to find the atomic economy. Atomic economy equation is atomic economy equals mass of the desired product divided by mass of all the reactants into 100. Right. Now our desired product is oxalic acid and its mass is given here. They say its 1 mole is 90 grams per mole. To get this 90 grams per mole, they have used this molecule, these two molecules. One is water. We know the molecular weight of water is 18. Other one is this one. Let's see. Here you have a carbon atom. Here you have a carbon atom. Here you have a carbon atom. It has only two bonds, so other two should be hydrogens. And here you have a carbon atom. So if I add them together, 1, 2, 3, 4, it has 4 carbon. That means 12 times 4, 48. Plus it has 1, 2, 3, 4, 4 oxygen. 16 times 4. No, not 4, 5 oxygen. 1, 2, 3, 4, 5. 5 oxygen are there in that molecule. So 16 times 5 means 80. Okay. Plus how many hydrogens? 1, 2, 3, 4 hydrogen. So hydrogen is 1. There are 4 of them. It will be 4. So our answer is 132. Mass of this one is 132. 132 plus 18, it will be 150. So simply atomic economy equals 90 divided by 132 plus 18 into 100. So when you multiply this one, is multiplied by 100, your answer will be, so I'll do 90 divided by 150 times 100. Your answer should be 60%. Okay, let's see whether our answer is correct. So atomic economy equals mass of the desired product divided by total mass of the reactants into 100. Yes, it should be 60%. Part B says give the laboratory reagents and condition required to convert glycolic acid to oxalic acid. Give the laboratory reagent and the condition required. Okay, now let's see what is this glycolic acid. So glycolic acid is something like this. One side is COOH group, so I put that COOH group on this side. So COOH. So I just put this COOH group into this side. Other side is CH2OH. That means other side is a primary alcohol. So to have this Oxalic acid, what you need is both side has to be COOH. So this side is already COOH, but other side also I have to convert into COOH. So that means this side I have to change it into another COOH. Right. So we have a primary alcohol and I want to convert into a carboxylic acid. Alright, that means it's an oxidation. So that means it's further oxidation, not for the aldehyde. We need the carboxylic acid. So therefore we have to say acidified potassium dichromate. Usually we use sulfuric acid to acidify it. H2SO4 with potassium dichromate K2Cr2O7 is further oxidation. That means simple distillation won't work. So therefore we need heat under reflux as the condition. So heat under reflux. So you can clearly see that. So potassium dichromate 1 mark, potassium dichromate and sulfuric acid both will give you 1 mark. Both has to be there. And heat under reflux. That's the second mark. So from that you can get the oxalic acid. Right. Sucrose is oxidized by concentrated nitric acid to form oxalic acid. Okay. Sucrose is oxidized by concentrated nitric acid to get this oxalic acid. Okay. Complete the equation for the reaction of 1 mole of sucrose with nitric acid. They say 1 mole of sucrose with nitric acid. Now you have to complete balance this equation. Give one observation that would you seen during this reaction. First you have to balance it. Then you have to give one observation. They say one like help us. They tell is 1 mole of sucrose. That means this won't change. It remains 1. Right. Now here I can see 36 HNO3. That means 36 nitrogen here. In the product side, there's only one place which has nitrogen. That's here. So this has to be 36 whether we like it or not. Right. Then if I take carbon here, there are 12 carbon. Here I can see 1 here and 2 carbon here. Right. So 2 carbon in this molecule, but I need 12 carbon. How to get 12? I have to put 6 here. 6 times 2 is 12. Now using nitrogen and carbon, I found 2 numbers. For the last number, I have to go for hydrogen. I don't go for oxygen because oxygens are everywhere now. But hydrogen is very straightforward. This side I have 36 hydrogen atom. 36 hydrogen. Here I have 22 hydrogen atom. Okay, 36 times plus 22. 36 plus 20, 38, 48, 58. So we have 58 hydrogen atom. Wait, I'll talk 36 hydrogen, 22. So it's 38, 48, 58. We have 58 hydrogen atoms. Out of 58 hydrogen atoms, I can see, let's see this side, we have 1 here, 2 here. 2 times 6 is 12. Out of 58, 12 hydrogen already we have. So if I subtract 58 minus 12, that should be the number of hydrogen we are supposed to have it here. So 58 minus 2 is 56, 56 minus so is 46. How do I get 46 hydrogen? To get 46 hydrogen, we need to have 23 H2O. 23 H2O will give you 46 hydrogen. Then they are asking give one observation that would be seen during this reaction. So we can see NO2 gas is produced. NO2 is a brown gas. Where did we learn NO2 is a brown gas? In a dynamic equilibrium reactions, and even for Kc and Kp also, we discussed that NO2 is a brown gas, and we talk about what will happen to the brown gas intensity and everything. So brown fumes of NO2 will be produced during this reaction. That's the one observation that we can see here. So it has given here as the answer. It says a solution of sodium hydroxide was titrated against 25 cubic centimeter oxalic acid. So if you look at the formula of oxalic acid, it has 2 COOH group. So this is a di-basic acid. It has 2 H plus ions. You can clearly see that. We learned that when anything has 2 H plus ions, sometimes they will neutralize in 2 different stages. Yes, I can see it. right? So we are adding sodium hydroxide. So oxalic acid means H2C2O4, right? So when I add sodium hydroxide, if it has two different endpoint means, first what will happen? First H plus ion goes with the OH minus ion forming water, right? Then what will happen? You get HC2O4. HC2O4. Why? Because one H plus ion go with OH minus ion. So the remain that place will be replaced by sodium. So that means when the first H plus ion in H2C2O4 get neutralized, you get the first endpoint. Then the second one, there's another endpoint. That means that's the where you will neutralize the second. I'll just remove the sodium, then it will make sense. Otherwise, it will confuse you. Okay. So we'll assume it gives only OH minus ion, sodium hydroxide. So H plus ion from our H2C2O4 goes to this OH minus ion forming water. So you will get as a product H2C2O4 minus, because H plus ion is gone. Now this H2C2O4 minus will neutralize with another OH minus sign. When you add another OH minus sign, what will happen? This H2C2O4 minus will get the second H plus sign, sorry, Hc2O4 minus. It should be Hc2O4 minus will get the second H plus ion, gives you C2O4 2 minus, and a water molecule is produced. So that means it's a neutralization of dibasic acid in two steps. So I can see that first rapid pH change take place between 3 to 5, roughly 3 to 5. We have learned, we know that methyl orange is the best indicator to find the endpoint between 3 to 5. We learned this one as a theory part. But in there we use a different acid. We use H2CO3, carbonic acid. But here is oxalic acid, but the story is same. Second one, rapid pH change start from around 6.5 to 12, but we know that what indicator will cover this region is phenolphthalein. So those things we know it. A student sketch a curve show the change in pH during this acid. So it's a neutralization of a dibasic acid in two steps. That's what happening here. Now keeping this in our head, we'll see what happens. Select one indicator for each equivalent point from this titration graph. Include the color at the end point for each indicator. Use your data booklet. Alright, so it's very easy, right? So we know that first indicator we had methyl orange, right? Methyl orange acidic color is little bit very close to red or pink. So methyl orange. So acidic color is red color. We know that methyl orange has an important part because it's always when its color change, our endpoint color is orange. So methyl orange endpoint color will be orange. But when it goes to basic side, it will turn into a little bit yellowish color. Right. Then we add phenolphthalein. When we add phenolphthalein, so otherwise you can use the data booklet. But phenolphthalein, if I take the color change, phenolphthalein, it shows pink color with basic medium. So in this side is colorless. So since it's colorless, so what are the color change I will see? When it goes to red to orange, I will stop the titration. Colorless to pink, I will stop the titration of phenolphthalein. But if both of them are in the same environment, for phenolphthalein, initial color will be yellow. Why is that? Methyl orange is there in the medium. No? Now let's see whether our question says both indicators are in the same place. Select one indicator for each equivalent point from this titration graph. Include the color at the end point for each indicator. Use your booklet. They are not asking color at the end point for at the end. So that's why they are not asking at the beginning, because the reason is at the beginning the yellow color of methyl orange can mix up with phenolphthalein. But here there's no problem. So first one, best indicator for me is methyl orange. So you can write the indicator as methyl orange. We know that for methyl orange, roughly as I remember, pH value will be 3 to 5. That's why we use methyl orange, color changing pH value. Color change at the end will be methyl orange, always endpoint color is orange. Then if you go for second indicator, We know that phenolphthalein is the best one. Phenolphthalein, roughly, as I remember, the color change in pH range is between 8 to 10. And you know that in basic color, it will show the pink color at the end point. So these are the colors we have to write for this titration. Next question they're asking, suggest a difficulty that would occur if both indicators are present in the same mixture. We discussed that part, because the reason is, if I go back to the same place, now if I use methyl orange here, methyl orange acidic color is red or very close to pink. Then it goes to the end point, it turns to orange. Then what will happen when the medium become basic? Methyl orange shows a yellow color. And then what will happen with the presence of phenolphthalein, it's colorless to pink. I think for phenolphthalein it's not a big problem for us, because phenolphthalein in this area is colorless. But let's assume a child take a different indicator. So if we take a different indicator, let's take an example of a different indicator. Instead of phenolphthalein, if you use phenol red, then in phenol red, both has a color. Therefore, what will happen? In phenol red, as I remember, is red color at the beginning. Yes. Phenol red, yes. Red and red to orange. Yes, there's a problem. So when you have red here and orange is your final color, but red and yellow mix here, it's like usually like orange. And the product is endpoint is also like orange. So since there are many colors, you will get mixed up. That's the one problem you will get when you have both indicators in the same container. So difficult to see the color change, colors will get mixed. That's the reason when you have two indicators in the same mixture. In this question, they're asking, determine by using the graph the two Ka values for oxalic acid. You must show your working on the graph. Right. Now let's see for this one. They're asking Ka values. We learned that in a weak acid and a weak base titration, half neutralization point. Now, this during a weak acid and strong base titration, during this area, why there is no change in the pH value? Because this area is creating a buffer system. This area is a buffer system. Any weak acid strong base titration, this happens. What is this buffer? Let's take this one. I'll take the first buffer system. We have oxalic acid, H2C2O4. When you react with sodium hydroxide first, what is going to produce is, now let's take it, you have little bit of sodium hydroxide. So little bit of sodium hydroxide means when the reaction is finished, sodium hydroxide is not there, because it's little bit, it's less. But what you get here is a salt, NaHC2O4 and water. That means in the final mixture, I have remaining weak acid. Why I say little bit? Because it didn't go for the endpoint. Before the endpoint is always you have less sodium hydroxide, because you didn't completely neutralize the weak acid. So weak acid is there, and we have the salt of the weak acid here. Weak acid and salt, a mixture of weak acid and salt, it is a buffer system. So pH value of such buffer system, pH equals pKa log concentration of salt divided by concentration of weak acid. Okay, that's the pH value. But there's a trick here. The catch here is when you take half of the neutralization point. Half of the neutralization point means dual. Now here you can see neutralization point is somewhere around 25. Half of it means 12.5. So I'll take the neutralization point 12.5 somewhere here, right? Okay. So this is half of the neutralization point. In the middle of the titration, concentration at this point, concentration of salt is equal to concentration of weak acid. Why? Because when you put half of the sodium hydroxide, half of, if you have C concentration, let's say you have 100 C, at the half of a neutralization, 50 of them go and produce the salt. And 50 of them remains here. The concentrations are same. So at the half neutralization point, concentration of salt equal concentration of weak acid. So if the concentration are same, now pH equals pKa log salt and weak acid concentration are equal means log 1. Log 1, if you type it in the calculator, is 0. That means half neutralization point pH equals pKa. If I find volume 12.5, if I read this pH value, you get pK value. If you know the pK value, you can find minus antilog to find the K value. That's the first K value. Second thing they same. Okay. Second neutralization point came at 50. Half of it means now the neutralization starts somewhere here from 25, right? Because the reason is it was starting the neutralization from there because first neutralization end, then you go there. From 25 to 50, the half point is again the volume is 25 no. So half exact midpoint between 25 and 50 is 37.5. If you find the exact midpoint is somewhere here 37.5. Okay, you take the 37.5, find the pH value. That's the second pK value. So if you know the second pK value, from that you can find the K value for the second dissociation. So you know the K1 and K2 for the neutralization of this acid. Okay, I'll explain it again. Now let's assume we'll forget about the second neutralization. We'll take the first neutralization. So this is a neutralization of a weak acid and a salt. Our weak acid is H2C2O4. And for that one, we are adding sodium hydroxide from the top. Butyrate, right? Let's assume I have 100 H2C2O4 molecules. It's an assumption. To neutralize this 100 H2C2O4 molecules, you need 100 sodium hydroxide molecule. Where did this complete reaction happen? At this point. That's why we have the end point here. So if I see it is 25 cubic centimeter. So that's where the neutralization takes place. But they are not asking what is the neutralization. They are asking us K value. So K value find there's a trick. The trick we have here is now we take half neutralization point. Half neutralization point means instead of adding 25 cubic centimeters of sodium hydroxide, I am going to add 12.5 cubic centimeters sodium hydroxide. So I'll just change this number. I said we had assumption is we had 25 molecules of H2C2O4. We add 25 sodium hydroxide to neutralize it because their ratio is 1:1. So that's the volume is 25. But let's assume instead of adding 25, if I add half of it, 12.5, whole H2C2O4 will not get neutralized. Instead of that, what will happen? They react with 1:1 ratio. No? Out of H2C2O4, we have 25, only 12.5 will react because we are adding 12.5 sodium hydroxide. We are adding half of this one. So 12.5 is somewhere here. Okay, this is the point we are adding 12.5. What is 12.5? If this is volume V, this is half of volume V. Right. When I add half of volume V, what will happen? Now sodium hydroxide will be completely react because we are adding less amount of sodium hydroxide, 12.5. Let's see what are the products we are going to get. So this will completely react, but here 25 minus 12.5 means another 12.5 is remaining. 12.5 H2C2O4 react with 12.5 sodium hydroxide gives you 12.5 salt, H HC2O4 and water. That means 12.5 of salt is produced. Can you see that? The salt concentration and the weak acid concentration is equal. Since the salt concentration and weak acid concentration, salt concentration and weak acid concentration are equal, this is a buffer system. So this whole area is a buffer system. Buffer system of a weak acid and a salt, there's an equation to find its pH value. You have to remember that equation. That equation tells pH equals pKa plus log salt concentration divided by weak acid concentration. So if I put the numbers here, which I use the hypothetical numbers, pH equals pKa plus log salt, I'll say, like, since both are in the same volume, salt concentration is 12.5 divided by whatever the volume. Weak acid concentration also 12.5 divided by whatever the volume. They will cancel out. So it's log 1. If you type log 1 in the period table, in the calculator, is 0. So therefore at this half neutralization point, pH equals pKa. So remember, if you see any weak acid strong base titration, if you find the exact midpoint of the neutralization, that means if we need V volume for the endpoint, if you take half of it, the pH value at that half neutralization point, there's a pH value here. No? That pH value equals to the pKa value of the weak acid. Remember that one. From this equation, we figure it out. So that's the pK1. They are not asking only for one pK. They are asking for another pK. That's the second pK. So next titration start as soon as you finish this endpoint. That's you finish the endpoint at 25 cubic centimeters. This titration goes till 50. That's the next endpoint. Okay. 25 to 50, if I find the range, there's another 25. Okay. The whole volume, total volume is another 25 cubic centimeters. Half of it means 25 divided by 2 means 12.5. For this 25, if you add another 12.5 to find the midpoint, we will get somewhere around 37.5. The volume should be 37.5. That's the next half neutralization point. At 37.5, if you read the pH value, according to this equation, that's equal to the pKa2 value. So simply what you have to do is find the midpoint here, volume, find pH value, you get the pK1. How to convert pK1 to into pKa1? You take minus antilog of it. So then you get the Ka1. Same thing you do it, you take the next titration, second one, take the midpoint of the volume, take the pH value at that point, you get the pK2. If you take minus antilog of that one, then you get the second Ka value. That's how you find Ka1 and Ka2. Right, if you do that one, as you have mentioned, the values will be Ka1 will be something around 0.05 moles per cubic decimeter. Or if you go for Ka2 value, it will be like 3.16 into 10 to the power minus 6, but they have given a range. So within this range, any value you are going to get, it will be accepted. Now let's go for next one. Next part is, it says spinach is one plant source of oxalic acid. Approximately 700 milligram of oxalic acid can be extracted from 100 gram of spinach. Okay. So if you take 100 grams of spinach, you get 700 milligrams of oxalic acid. High performance liquid chromatography HPLC is used to analyze in the extraction process. The HPLC equipment is connected to a detector which record peaks when substance pass through the HPLC column. Suggests how a pure sample of oxalic acid would be used in identify the oxalic acid peak at the chromatogram of the spinach extract. Right, we know that in HPLC, usually to identify any substance, I'll just remind you what was HPLC. We had like a burette-like column, and there was a polymer beads which are packed over there. Then what you do is you put the mobile phase with the sample. Then the retention time is the one which tells us whether our substance is pure or not. We can identify this one. So they are, even though they are talking about huge details, they are asking whether you know HPLC. And in HPLC, what was the factor that we are going to measure? The retention time. So retention time is the one they were asking here. So using the retention time, we can find whether the oxalic acid is pure or not. So if it is right retention time telling me the data booklet, we can identify our oxalic acid is a pure one. So that's how we can identify the oxalic acid. In this one, it says a 0.558 mole per cubic decimeter solution of oxalic acid is used for cleaning. Okay. Calculate the mass of spinach required to make 500 cubic centimeter of this oxalic acid cleaning solution. First, we'll see, because they are saying that first we'll put the data we have. They say that in 100 grams of spinach, we have 700 milligrams of oxalic acid. So we'll write that one. If we take spinach 100 grams, I will get inside this there's 700 milligrams of oxalic acid. Oxalic acid means H2C2O4. H2C2O4. Right. Now let's see what is this question is about. A 0.558 solution of oxalic acid was for cleaning. We need mass of spinach to make 500 cubic centimeters of this oxalic acid. 500 cubic centimeters of this oxalic acid, 0.558. So I want to make 500 cubic centimeters of H2C2O4. The concentration is 0.558. So we have 0.558 moles per cubic decimeter. H2C2O4. Okay. Now when you have the concentration and volume, we'll do step by step. First step, what I'm going to do is I'm going to find number of moles of H2C2O4 oxalic acid. Number of H2C2O4 moles. We know that C equals N divided by V. So therefore N equals C times V. So N equals C is 0.558 multiplied by volume is given 500 divided by 1000. Okay. So let's see 0.558. 0.558 0.558. Our answer is 0.279. 0.279 moles. We don't need number of moles. We need the mass. So we know how to find convert the number of moles into mass. That's the second thing I'm going to do. Second thing, mass of oxalic acid H2C2O4. Number of moles equals mass divided by molar mass. So therefore mass equals number of moles times molar mass. Number of moles of oxalic acid is given 0. We found it 279 moles. And the molar mass of oxalic acid was given at the beginning of the question. I can remember it. It was 90. Otherwise you can calculate it. 2 carbon means 24. 24 plus 4 oxygen. 64. 64 plus 24 is 68. 78. 88 plus 2 90. Yes, it's 90 grams per mole. Right. If you multiply 0.279 by 90, 25.11 grams. So mass required is 25.11 gram. So I need 25.11 gram of H2C2O4. But they say if you use 100 grams, you get 700 milligrams. 700 milligrams means we are getting actually 0.7 grams. So 100 gives 0.7. So we need to get 25. How much you need? Let's say 25 has how many 7? So, okay, 25. So we need to find mass of spinach. We need. How to find it? Now, 25.11 means how many 0.7s? Let's find that one. So 20.5, 25.11 has how many 0.7 grams? So what you're going to do is, right, 25.11 we are going to divide by 0.7. 25.11 divided by 0.7. We have 35.87142857. Alright, so 25.11 contains this many number of 0.7. So to get one 0.7, we need 100 grams. To this many number of 0.7, what I am going to do is, I am going to multiply 100 by 35.87142857. Then when I multiply it, what we are going to do is, I'm going to multiply this by 100. I need this many grams. 3587.142827 grams, or you can write it, we have rounded it up now, we can write it 3.59 into 10 to power 3 grams. That's why we can get the answer. Now we'll go for the answer. So we are expecting 3.59 into 10 to power 3 grams. 3.59 587 3.59 into 10 to power 3 and 3590. Yes, that's our answer. That's what they are expecting us to find. So okay, write the equation for the reaction of oxalic acid with excess phosphoric 5 chloride, PCl5. So oxalic acid with PCl5. So we know that oxalic acid, so if I write the equation, they are not asking the displayed formula of anything. So we'll write the normal structural formula that we use. Oxalic acid is a dicarboxylic acid. When you add PCl5, what will happen? PCl5 chlorine atom will replace the OH group. So you get COCl. You have to remember the byproduct. POCl3 plus HCl. It's a different color. So plus HCl. But here it's not only one OH group. There are two OH groups. So therefore you need two PCl5. Because both COOH group has OH group. So both of them will get replaced. Then you'll get 2 POCl3 and 2 HCl molecules will get produced. Then we know that this is the equation. There's acid chloride products. That's correct. Acyl chloride product. and the balance equation. Then you get the 2 marks.